Hey guys, welcome to this Mometrix video over acceleration of gravity. Now, before we jump into the acceleration of gravity, let's talk about acceleration real quick before we move on to the phenomenon of gravity. In general, acceleration refers to any time there is a change in velocity. So if you speed up, you are accelerating. This may sound like common sense because of the way that we use acceleration in our language. If you're driving in the car and someone says accelerate, we generally think, oh, they're asking me to go faster. But here's why this may be potentially confusing for someone who is very much in tune with the precise definition of acceleration. Slowing down is also accelerating. So you're accelerating when you're speeding up, slowing down, and or changing directions. Because remember, acceleration just refers to the change in velocity. So if velocity is not changing, then you're not accelerating. For example, when you're driving down a straight highway and you set your car on cruise control at 65 miles per hour, the car is going at a constant velocity of 65 miles per hour and therefore not accelerating. It's not changing in speed or direction. Pay attention to this. An object may be at a constant speed, but if it changes direction, then it's acceleration. An example of this is the orbiting of a satellite around a planet. Its speed is constant, but it's constantly accelerating due to the constant change of direction. Acceleration is specifically defined by the rate of change of velocity. So in equation form, it looks like this. Now let's break this down a little further. So acceleration is equal to the change in velocity over the change in time. Well, change in velocity specifically means the difference in initial and final velocity. So you start at this velocity and then the velocity changes to this other velocity. And this all happens within this specific time frame. So that is acceleration in a nutshell. Now let's look at acceleration of gravity. Gravity is actually still kind of an enigma to physicists and scientists, but we still have some numbers that give us a little insight into this mystery. Here is what we know. When we have an object that is free falling, so let's say something has been dropped from high up, well, this falling object has an acceleration of 9.8 meters per second squared. This number came from a lot of other really intelligent people who discovered that the acceleration of any object because of the force of gravity anywhere on the Earth is 9.8 meters per second squared. And that's basically what we know. But this one bit of information has lots of useful applications for us to be able to solve problems. To start, let's look at a few laws. Newton's first law of motion, also called the law of inertia, states this. An object at rest remains at rest, and an object in motion stays in motion with the exact same speed and in the same direction unless it is acted on by an unbalanced force. An unbalanced force literally just means that the force is greater than or less than the force being exerted by the specific object. If the force acting on the object was equal to the force being exerted by the object, then they would just cancel each other out and therefore stay in rest. Now, the reason this law is relevant to us learning about the acceleration of gravity is because this unbalanced force that acts on this object is the very thing that causes acceleration. The force causes a change in something's velocity, which, if you recall, is the definition of acceleration. So, like in our example of a satellite orbiting around the planet, the reason that it orbits and doesn't just float off is because of the force of gravity from the planet that is pulling it towards itself and causing the satellite to constantly accelerate. So that's Newton's first law. It gives us this idea of when something will accelerate or what it is that specifically causes things to accelerate. However, Newton didn't stop there. He told us that in order for something to accelerate, it needs to have an unbalanced force acting on it in his first law. But he goes on to explain just how much force is needed in order to cause an object to accelerate in his second law. So you can think of Newton's first law as qualitative and his second law as quantitative. Here's what Newton said in his second law. The acceleration of an object depends directly upon the net force acting upon the object and inversely upon the mass of the object. So mass basically refers to how much material an object is made up of and allows us to determine the inertia of that object. Newton's second law tells us that if I take an object with a relatively small mass, let's say a bottle of water, and an object with a relatively large mass, let's say a water tank, and apply an equal force to them, then the acceleration of the object with a larger mass, in this case the water tank, will be smaller than the acceleration of the object with a smaller mass, in this case the water bottle. So if the same force that is applied to the water tank to make it move is then applied to the water bottle, then the water bottle will go pretty stinking fast. So if the mass of an object increases, then the acceleration of that object is decreased. Here's the kicker, and why acceleration of gravity is kind of its own category of acceleration. Kind of. Despite the mass of an object, all objects freefall with the same acceleration, which is 9.8 meters per second squared. The term freefall just means that an object is falling with no other force acting on it or against it, except gravity. No air resistance, nothing. Just gravity. Let's take the two objects that we've already looked at and insert them into our freefall scenario. So we have our water tank with a mass of 19,000 kilograms. And let's say we have a 1 liter water bottle. So it has a mass of 1 kilogram. Well, if we considered Newton's second law of gravity and implemented it into this problem, then it would seem as though the water tank would have a greater force of gravity acting on it, causing it to hit the ground before the water bottle. If this consideration seems correct to you, then you're halfway right. The object with a greater mass is experiencing a greater force of gravity, but it does not cause it to hit the ground before the object with a lesser mass. Confused? That's okay. Let's look closely at Newton's second law. It states that the acceleration of an object depends directly upon the net force acting upon the object and inversely upon the mass of the object. Well, when examining the acceleration of an object, you must consider two factors: the object's force and the object's mass. When implemented into the water tank water bottle scenario, it would be accurate to say that the water tank experiences a far greater force, which often leads to increased accelerations. Nonetheless, an object's mass resists acceleration. Therefore, the water tank's greater mass, which often leads to decreased acceleration, counteracts the effect of the force. It is the force to mass ratio which determines the acceleration. So even though the water tank encounters way more force than the water bottle, it also has way more mass than the water bottle. The force to mass ratio is the same for each. The greater mass of the water tank demands the greater force so that it can maintain the same acceleration as the water bottle. And that is why they both reach the ground at the same time. I hope that this video over acceleration of gravity was helpful to you. If you enjoyed it, then be sure to give us a thumbs up and subscribe to our channel for further videos. See you guys next time.